I think I've got the people who just spoke up. Okay. Let me get my OneNote up and going. Okay. Can you see this? Hopefully you can see my OneNote. It's got math on it.
Yeah.
Wonderful. Okay. Let me see if I want to. Let's go back to where we were. So I think this is more or less where we left off. Here was the homework that I assigned. I asked you to read over theorem 1.5 on page 31 and look at the examples 3 through 5. And then I gave you these 5 problems to do. By the way, still having trouble with the homework, so just hold on to it at this point. But let me go over this. Did you do this? Did you read theorem 1.5? Were there any questions on that? And did you go over any of examples 3 through 5? And if you had any questions on any of them, this would be a good time to bring it up.
Can you go over example 5?
Sure. So the request for 5. Let me flip around my tablets and my mouse here. This goes here. So, okay, so why don't I record this before I leave the page, because sometimes it's hard to come back to a page. So I've got a request for number 5 on these pages. What about the homework, since we're here for page 34, 4 and 5, page 22, 18, 19, and 20? Any requests to see any of those?
Um, 5A and number 20.
5A on page 34, is that what you're asking? Because I'm not
Yeah.
sure. Okay, so page 34, 5A. I'm not sure what that's about, but I'll be happy to look at it. Okay, so we've got, well, both questions involve number 5, but different number 5s, right? Number 5 on page 32, I suspect, and 5A on page 34. Is that, are those the 2 requests? I think so. Okay, great. So let's turn to those. To do that, maybe I'll just add a page here. Okay. So let's go back to page 34 and look at 5A. So 5A, it says in each part, determine whether the given vector is in the span of these other 2 vectors. Okay, so So asking whether this vector is in the span of S is the same as asking, is the vector 2 minus 1, 1 equal to some constant or scalar 1, 0, 2. Plus some scalar times negative 1, 1, 1. And I think it's assumed throughout here that we'll be looking at A and B real numbers. Okay, so this is what this linear combinations of this form where A and B are in R is what we're talking about as a scan. And we're asking whether 2, negative 1, 1 could be written in that way. Now there's two ways to go. The one way is the formal way that we've been doing in class, which is to turn this into equations and then simplify the system of equations to get a solution of A or B or not. So there's the method. Let me just call that the method, which I'll come back to in a moment. But before I even look at the method, there's always this an educated guess, which you can do sort of just by trial and error. So is there a way to get this just to work out by trial and error? So for example, having a 2 here, if I were to pick A to be 1, and this is just trial and error, then in order to get the 2 here, I would have to choose B to be what? Negative 1? Why? Because if B is negative 1 times negative 1 would be 1. And if you add that to this one, you get 2. So now you can say, how did I get A equal 1? And that would be the trial. I'm doing a sort of an educated guesswork here. Now, with that as a guess, we can check whether it works in general. But certainly, so this is my guess. To check whether it works, let's just put the 1 in here. So it would be asking is 1, 0, 2 plus, and if I make this negative 1, then this becomes really negative 1 times negative 1, 1, 1. And if I do that, do I get this? Well, I know that the first component is going to work because 1 and 1 is 2. So this one works. This was a 1 in front, so you can't even see the constant. Okay. If I look at the second component, 1 times 0 is 0. And negative 1 times this is negative 1. So that works. So this is promising. And now 1 times 2 is 2. Minus 1 is 1. Whoa, that was quick. Okay, so that's not the way the method went, but there's nothing to stop you from taking an educated guess. Once you see that it works, then the answer is yes. Now, if the answer were no, suppose one of these, the first one, why do I say it was an educated guess? I picked A and B so that the first component worked, right? So 1 times this plus negative 1 times that, I saw 1 and 1 would equal 2. So I made that as my educated guess. And then afterwards, I just verified that the rest worked. If it did not work, then I have a choice. I could make a different guess. So this is really guess and check, which is a technique you even see in calculus. You try to integrate something, you can guess and just see if what you have is the derivative is what you want it to be. Okay, but does everyone, I don't think I talked about this method before. But there's nothing to stop you from doing guess and check, especially if you're trying to do something quickly. And if you're fortunate and a good guesser, then you could guess the answer immediately. Let's go back and do it using the method now. The method would be what? 2 would have to be equal to this times this plus minus this. So that would be the first equation you get from this equation holding. -1 would have to be equal to what? -1 would have to be a times 0, which is 0, plus b times this. So this one just tells you what b is, so it's not that much longer actually. And then the third equation would be 1 would be what? Equating the components is what we're doing here. You would get these equations. Now you could fiddle around and do try to introduce all the zeros that's described in the book, but there's really little reason to do that because this is immediately telling that b is -1. And if b is -1, you could put that into here. So 2 would equal a, negative a -1 would be +1, which would imply that a is 1. Which is the same answer I got by educated guesswork. Does this make sense? 2 methods to do this.
Yes. I had accidentally put -2, and that's why I was getting it wrong.
Oh yeah, well okay, that happens all the time, especially to me and maybe to some of you too. If you write the problem down wrong. By the way, that can happen on a test. It's particularly annoying when it does happen, right? If you write the problem down wrong and you get the wrong answer because you wrote the problem down wrong, usually if you've done that and there is no solution in that case, for example, usually I'd probably give you a lot of credit because that's just a simple, you may have had the right idea, but you just may have written the problem wrong. So usually my rule is if you change the problem unknowingly, but the problem that you make is roughly at the same level of difficulty than the original problem, then I'll try to give you full credit or nearly full credit if you know what you're doing. Sometimes people write down the problem wrong and make the problem trivial, and then I can't do that. Okay, so that was that. The other one was what? Page 31, number 5, I believe. So let's go back to that. So this was off the reading. And I guess you're asking for an explanation of example 5. Is that on page 32, I think? So let me make sure I have the right problem. They give you 4 matrices, and you're in the vector space of M2 cross 2R, which means matrices that are 2 by 2 with real numbers. And they want to know a matrix in there can be expressed as a linear combination of 4 matrices as follows. Oh, okay, and this is like all these problems. Here they give you the constants. So here you also have a choice, but we're looking at number 5. I'll scan down a little further. Hopefully I have room to do that. That'll work. So we're looking at number 5 on page 32. And there, they basically give you this. That A1, 1, A1, 2, A2, 1, and A2, 2 is equal to 1/3 A1, 1 plus 1/3 A1, 2 plus 1/3 A2, 1 minus 2/3 A22. So it's that coefficient times matrix. Or 1110. Plus by the way, this is easy to mess up. So if I mess up a sign, please let me know. Or any other aspect as far as that goes. Okay. Quickly looking it over. It looks okay, I think. So it says the matrices generate M2 plus 2 since an arbitrary matrix can be expressed in this way. Okay, so what are you to think when you see this? Well, there's two things to think of. This is supposed to be an example of the previous theorem, theorem 1.5. So the span of a subset of the vector spaces is a subspace. Okay, so that's what this is sort of supposed to be about, but how did they come up with this? Well, so there's two questions. How did they come up with this? So how? And the answer to that is probably the same way that we've done everything else. So we can write A11, A12, A21, A22 as some matrix, let's call it, we call it little a times times 1, 1, 1, 0 plus b 1, 1, 0, 1 plus c 1, 0, 1, 1 plus d times 0, 1, 1, 1. So they started off essentially assuming that this matrix can be written as a linear combination of these four. And then they were able to solve. So what is this going to give you? If you go through this usual solution method, A11, for instance, I'll just write down the first equation. I don't think I'll do it in detail, but this is the kind of thought process that's involved. A11 would be equal to A times 1 plus B times 1 plus C times 1 plus D times 0. So if I look at this as the first component of the first entry of the matrix, it would be A times that plus B times this plus C times this plus D times that. So that would give you an equation for A11. And you're supposed to be thinking of these as known and these as unknown. A, B, C, D are unknown, but they're real numbers. Okay. So you do this for each component. You get 3 other equations. So when you're all done, let's just go through what's the last one, for example. The last one would be A22, which would be A times 0. It would be B times 1. It would be C times 1. And it would be D times 1. So this is the last of the 4 equations. There are 2 more in the middle that are done in a similar way. You have 4 equations and 4 unknowns. And then you go back to the method that's been described in the book already of introducing zeros by adding and subtracting equations. And in the end, getting a system of 4 equations that will be easy to solve. Okay, so that's how one could come up with this. And when you do, it turns out that that's what's in the parentheses is A, and what's in the parentheses here is B, and what's in the parentheses here is C, and what's in the parentheses here is D. And I already lost some stuff here. Gotta be careful. So that's plus here. And I think there was a third here, probably with a minus. It was minus 2/3, sorry. I want to stay there. Okay, so those are what A, B, C, and D. So those are the results, and that's from solving the system. So you have a choice. You could either solve the system again yourself and actually come up with A, B, C, and D being what I just said, or you could simply verify that it works. Okay, so verify, oh, well, it's not going to be easy to verify because as I look and looking at this, it's disappearing before my eyes, unfortunately. Let me try to, let me see, 1/3 A11 minus 2/3 A12. And then what else was there? 1/3 A21. And yeah, so rather than solve it all, well, let's just see how it would work if you took this times 1, added this to that times 1, added this C to that times 1, and all of this times 0 is 0. So we just have to make sure that we believe that if you added up A and B and C, you do get 1. Well, let's see if we can see that. Well, first of all, yeah, because 1/3 A11, another 1/3 A11, and this is another third A11. Got melted away on me, but it was there. That adds up to A11. So then it would just be verifying that everything else cancels, and it does. 1/3 A12 and another 1/3 A12. Together, that gives you 2/3 A12, and this cancels that. So when you add up what's in the of A, B, C, the second term of each of them, you'll get 0. Same thing should occur in the third column. This one and this one and this one give you 0 because the 1/3s combined to cancel the minus 2/3. What about the last row, minus 2/3 A22, this and this cancel as well. So what I've just gone through is a verification that this works for A11. So you
Does it work for A12?
say it again.
So you have the 0 for negative 2/3.
You mean, where are you at?
For A12,
A12, but in which one of these,
the third one you have a 0. The negative 2/3 multiplies with the 0.
uh,
So yeah,
no, let me see. We're finding, we're taking all of this times the first term, which would be, we're just doing this one. So it's multiplying 1. All of, I'm
oh,
just,
okay. Yeah, I think you're doing the second one. I was talking about A12.
no, I didn't do that. I didn't get that far.
Oh,
So
okay.
I'm just checking the first entry. So it would be all of this times 1, all of this stuff times 1, and all of this stuff times 1. So that means you just got to add up A and B and C and see what goes on. And if you do that, these three give you A11, but all the others give you 0. You see what I'm trying to say there? That should work for the other. So if you wanted to do this one next, suppose you wanted to do this one, A12, then you would have to multiply this times this, and that would just be A. And then you'd have to multiply this times 1, so that would just be B. And then you'd have to multiply this times 0, and that would give you nothing. And then you'd have to do this one times this, which would give you D. So what you're really checking then is that equal to A12. Now let's check it quickly. If you add up, so this is A, this is B, and this is D. If you add them up, the A11 terms cancel. The A12 terms, let's see. So which one are we doing? A, B, and D. So this,
Yeah, that's the one I was talking about.
yeah, this, and this gives you A12, and the others cancel. Do you see what I'm trying to say here? Or did I lose you? I think it's Juan. Juan, are you okay on this?
Yeah, I'm good.
Or maybe it wasn't Juan who was asking me, but anyway, it looks like this works as well. And all 4 of them should work. So in this case, when I ask you to read it and just make sure it makes sense to you, here they already did the method to come up with the coefficients. So I think it's probably easier just to check that if you do what's indicated here, you'll get the right entries of this matrix over here. I did 2 out of the 4. I think you can do the other 2 in a similar way. Questions? Now they do say something else a little more interesting afterwards. On the bottom of this example 5, they say, on the other hand, the 3 matrices as they give there do not generate because each of these matrices have equal diagonal entries. Ah, okay. So what they're saying, that's an interesting way. So the second question on this part, and I'm not sure if we got this far, but we might as well explain what it means. So the second part of this, what they're saying is you cannot, they're saying the following, that second part, A11, A12, A21, A22, cannot be equal to A times, oh, this one, plus B times 1101 plus C times the last one, which is 1011. So they're saying that you can't always come up with anything that looks like this just using these three matrices. Now, it's true that you can get a lot of different things by using these three matrices, but what they're trying to tell you is you won't be able to get something that looks like the following. This matrix in particular will not be equal to. So you're trying to say this is in general, there's an inequality here. And I'm making it more specific. So you won't be able to get this. And the reason you won't be able to get this is whatever, when you multiply A times this, you're going to get something that looks like what? A0, 0A. And when you multiply B times this, you're going to get something that looks like what? B, B, 0B. And when you multiply C times this, you're going to get C0, CC. Okay, so when you do that, notice what you're coming up with. The first entry will be A plus B plus C. The second entry, I guess, would just be what? B. I suppose that's right. This entry here would just be C. And the final entry would be A plus B plus C. So what this shows is that whenever you add A times this plus B times this plus C times that, what you come up with is a matrix that looks like this. And there's no way that's going to be equal to this. Why? Because this on the diagonal has equal entries and this does not. So if you're taking a linear combination of these three matrices, you're always going to get something that has equal entries on the diagonal. In this case, A plus B plus C. So that means you can come up with a matrix which does not have equal entries here. I just made one up. And that means you can't get all matrices of this form. You can get some, but not all. That's the last part of this. And that's what that's the kind of thing I was hoping you would do. Any questions on this? Cool. Then let's move on. Maybe before moving on too far. So maybe you can help me. The homework that I just have been talking about, what was the assigned problems in 1-4? So what was the homework that I just assigned? I guess I could probably just pick it off if I go back on the sheet. Let's see.
In
It was-
section 4 and 5.
I'm sorry, it was what, 4 and 5?
Yeah.
Thank you. Okay, so let me give you a few more because we've done 1 through 3 before and we did 4 and 5. There's a host of a lot of problems here. There's all the problems on page 35. Probably we should do the ones that have daggers. Why? It doesn't mean a dagger doesn't mean it's going to kill you. A dagger in this book means that the problem is needed for something in the future. Okay, so I'm looking on page 35. The ones that have daggers are 11 and 13. By the way, 13 has a place for you to visit in order to see how to solve it. I don't know how that works out, but here's new homework. In section 1.4 again. Do those two problems at least, 11 and 13. (14) and 15 look like they may be interesting as well. 14 and 15. Okay. So I think we're out of 1.4. Let's go into 1.5. So I'm flipping the page. And maybe just for time's sake, I'll go straight to the definition. Normally I would take a little more time, but let me see. Let me flip the page here. Yeah. Yeah, maybe it's worth doing the example that they have there. So, all right, I'll do that. So we're moving on to section 1.5. It says, suppose V is a vector space over an infinite field. Why don't we assume as usual that the field is the reals? So we're into 1.5. And the field F is the reals. So V has an infinite number of vectors. V is a vector space with an infinite number of vectors. So we're assuming that V is not the, well, yeah, it could even be the zero vector space. If it were just the zero vector space, then it wouldn't have an infinite number of vectors, right? Because then everything would be that. But if it had at least one non-zero vector, so suppose X was in V and X is not the zero vector, then when you multiply that by any scalar, this will give you vectors that are different than each other, right? So for example, 1 times X would not be equal to 2 times X. We're assuming X is not the zero vector to begin with. So we're looking at a vector space over a real line. And what they say on the top of page 36, it is desirable to find a small finite subset. Or what is W? W is a subspace. So we have this set up. W is a subspace of V. And it is desirable to find a finite subset S of W that generates W. That generates means that you're in the span of that set. Indeed, the smaller S is, the fewer number of computations required to represent computers. So here's the example they want to consider. Suppose W is actually a subset of R3. Okay. And suppose S has 4 vectors in it. The vectors are U1, U2, U3, and U4. It says, consider, for example, the subspace W of R generated by S. And then they tell you what these 4 vectors are. So they tell you in this case that U1 is 2, -1, 4. They tell you that U2 is 1, -1, 3. They tell you that U3 is 1, 1, -1. And they tell you that U4 is 1, -2, -1. So there are 4 vectors in R3 that look like that. So what are we knowing? We're knowing consider the subspace generated by these. So their notation for that is back in where we were. Let's go back and pick up that notation. So this on page 31, the span of S is equal to W. So what do we know? We know that the span of the set S. And that's going this way well. So what does the span of S look like? It looks like all vectors that would be equal to A times U1 plus B times U2, all linear combinations of these 4 vectors. C times U3 plus D times U4. Such that what? A, B, C, and D are all real numbers. So if you collect all vectors that have that appearance, that are linear combinations of the 4, that's what we're calling the span of S. So S looks like this. It just has these 4 vectors in it. But the span of S has many more vectors. It's all linear combinations of them that look like this. So that's what we're assuming. Okay. Let us attempt to find a proper subset of S that generates W. So definitely, oh, how do we, this is a subspace. What is W? In other words, the set of all linear combinations like this. Why? This is a subspace by theorem 1.5. That's the one I asked you to read. Whenever you take a span of some collection, it forms a subspace. Okay, so that's the content of that theorem. And now what they're asking for, they want a proper subset of S that also generates. So a proper subset of S that also generates W. So what does a proper subset mean? A proper, let's see, did they give it a name? The search, no. Let us attempt to find a proper subset. The search for this subset is related to the question of whether S is a linear combination of other vectors in S. Okay, so they didn't give it a name, but let's just make sure we know what we're talking about. A subset, well, we got S, why don't we call it, S1, a proper subset, S1. That means S1 would be a subset not equal to S. So what would the subsets of S be? Well, you might just have U1, U2, U3. That's the proper subset. Or it could be U1, U3, U4, or it could just be U1 and U2. There are a lot of proper subsets, but the Venn diagram looks like this. If this is S, then S1 would be a subset of it. So there are things in S that are not in S1. That's what I'm saying, that S is a subset, but not S1 is a subset, but not equal to. Okay, so they're looking for a proper subset so that the span of S1 is still W. That's what they're looking for. Smaller, a subset of this whose span is still the whole subspace. And what they say in their explanation, they're saying the search for a subset, the search for the subset is related to the question of whether one of the vectors in S could be a linear combination of the others. So for example, suppose U4, the fourth vector here, could actually be a linear combination of the other three. So suppose that would happen. Then you wouldn't have to take linear combinations. Okay, so back in here, if this were true, suppose this condition were true, then this linear combination here, AU1 plus, oh, I guess I have a little problem here. Oh, that's okay. I'm using A1, A2, A3. That's fine. AU1 plus BU2 plus CU3 plus DU4. Things that are in the span of S, since U4 can be written this way, you can simply substitute that in. And that would mean what? You can write it as AU1 plus BU2 plus CU3 plus D, and you can put in this whole linear combination here. AU1, let's say 1U1, A2U1, U2 rather, 3U. And the, D times A1 U1 U2 U2 plus A3 3. So if the U4 vector was a linear combination of these, what would that mean? That would mean that you could really write any linear combination of all four of them just in terms of 3. How so? Well, you can combine this one and this one. And what would you have? You have A plus B, A1. I'm combining these two terms times U1. And then this one would be combined with this times the D as well. So that would be what? BU2 plus BA2 times U2. And then finally, the last one would be this one. So that would be Z. Oh, this is wrong.
Wouldn't it just be B in the parentheses and not BU2?
Thank you. Yes, and so this would be C plus D A3 U3. Okay, so if you were to know that U4 was a linear combination of the other U's, you can put that into this, and then you could realize that the linear combination of all four of these vectors is equal to the linear combination of just the first three. What does that mean? That means something that's in W, which is, something which is W, which is in the span of S, could actually be thought of as being in the span of this smaller set. So what would the smaller set be in that case? In this case, S1 would be just what? U1, U2, U3. So by taking linear combinations of these, you would be able to get all the linear combinations of the original set. So you're trying to minimize the set S to a smaller set. Now, of course, it may not be, this, I just assumed this. It could be something different. It could be that U1 is a linear combination of U2, U3, and U4. So the one of these U's could be in terms of the other three. It doesn't have to be this way. But no matter which way it would go, you would only have to take the span of a smaller set, in this case, a set having 3 vectors rather than 4. So that's what they're interested in doing in this section. If you have, so to repeat, if you have a subspace, which is the span of some set of vectors, you're trying to see if there's a proper subset of that set of vectors that give you the same subspace, and that's along these lines. Well, let's do the example to become a little more clear. So in the example case, these were the values that we have for U. U1, U2, U3, U4. And so they're pursuing this further, and they're actually looking for, is this possible? Is it possible that U4 is equal to the span of the U1, U2, and U3? And in order to answer that question with these vectors U as given, let's see. Yeah, what they're saying is U4, which is, let's just write it out, which is 1, -1, -1. Yes. So we're looking to see if 1, 2, -1 can actually be written as A1 times U1. But U1 is 1 minus 1, 4. 1 minus 1, 4. Plus A2, U2, and U2 is 1, -1, 3. 1, -1, 3. Plus A3 times U3. And U3 in this case is 1, 1, -1. Okay, so this is the question. Is it possible to write U4? So keep in mind, this is U1, this is U2, this over here is U3, and this is U4. 4 was 1, -2, -1. Can you write U4 as a linear combination of the previous ones? U1, U2, U3. And you could do that in the usual way. So if you made a system of equations out of that, yeah, then making sure if I would have done.
Professor,
Yeah,
U1 is 2, -1, 4.
U1 is 2, -1, 4. That's my problem. Thank you. 2, -1, 4. Thank you. Do I have any other problems here? Easy to mess up with some of the numbers. Hopefully the rest are correct. Okay, so if you're asking whether this is possible or not, then using the method from the previous section, it would be possible if you have this equation. 1 here would have to be 2a1, first component, plus a2. a2 times 1 is just that, plus a3. So this would only be possible if that equation can hold. And they put the 1 on the right side, which is just fine, doesn't matter. And the second components would have to be equal as well. So -2 would have to be equal to minus a1 and minus a2. This times this, and this a3. Double checking to see if that's what they have. It is, okay. And then finally, the -1, the third component would have to be a1 times 4, which is 4a1 times that, plus a2 times 3, which would be 3a2. And then a3 times this, which would be minus a3, and that would have to be equal to -1. So we box these equations, that should match what's going on in the book. And it does. Okay. And then the reader, then what does the author say? The reader should verify that no such solution exists. Okay, so call that a homework problem. Verify that this system of equations has verified this system has no solution. Okay, so that tack that onto the homework because that's what it's doing for us. This, however, does not, however, answer our question of whether some vector in S is a linear combination of the other vectors. So what we're trying to see here is if U4 is a linear combination of the other 3 vectors, U1, U2, U3. And the author is saying that if you try to solve that as a system of equations, you're down to what's in the boxed equation. And he's saying that this doesn't have a solution. So that means U4 cannot be written as a linear combination of the others, which means if you formed the set S1, it won't generate the same subspace. But he's saying all you've really shown is that U4 is not a linear combination of the others. Maybe some other of the 4 vectors is a linear combination of the remaining 3. And that's what he's doing in the next paragraph. Well, he actually shows. He says, even though this doesn't work, you can actually show. What is that going to mean? Another homework problem for you. It can be shown that what? U3 is actually equal to 2U1 minus 3U2, 2U1 minus 3u2 plus 0u4. Well, okay. So rather than give you another homework problem here, let's just verify that before we close this out. This should be easy enough to verify, which is easier than actually establish, right? To verify it, you would just have to show that U3, hopefully U3 is what I've written here, which is 1, 1, negative 1. Hopefully that's twice U2. U2 would be this, 1 minus 1, 3. Minus, no, that's, yeah, that's not U1. U1 is, according to this, 2, negative 1, 4. And then what? Minus 3 U2. U2 is this. 1 minus 1, 3. And this doesn't matter what U4 is because it's being multiplied by 0. So let's just check whether this all works. This should be easier to do. 2 times 2 is 4, minus 3 is 1. So that's matching this. Minus 2 plus 3 would be 1 also. That's verifying the second component. And 2 times 4 is 8. Minus 3 times 3 is 9. So it'd be negative 1. That's this. Okay. So you don't have to do that as homework because I just verified it for you. And it's true. Now you could say, how did they find it? And then the answer would be, so, okay, I verified it, but if you were to ask, how did they find it? They took, they started assuming what? Something that U3 was some number, let's call it B1 times U1 plus B2, B2 plus B3, B3. So instead of assuming what they did above, that U4 was a linear combination of U1, U2, U3, they investigated whether U3 is a linear combination of U1, U2, U3, and it turns out it is, and it turns out a solution to that would have B1 being 2, B2 being minus 3, and B3 being 0. Okay, so what does it all mean? So that means now, instead of starting with the original set S, which had U1, U2, U3, U4, we would, and we know that if we took the span of that set, we get W. What we're saying is S1, if we just restrict this down to being what? U1, U2, and U4. This is a proper subset of that. Why? Because everything in here is in here, but this has more. What does this have more? It has U3, which is not apparently in here. But even though U3 is not listed in here, what is true when you take the span of S1, you still get the same as the span of S, which is W. Which means you can do what we were trying to figure out. Is it possible to reduce the set of vectors in S to a proper subspace, a proper subset rather, whose span is the same as the original set? And the answer in this case is yes. Now, we're out of time. So I guess what I'll do, since, by the way, today I can't even stay after class, unfortunately, I have a department meeting. But, so I've given you some problems to do already, and then there's a verification problem here to do. And I would just say, finish up the reading here. So if I had another 5 or 10 minutes, I would say just read what's on page 36 and 37. I'll pick it up from there. question becomes, how do you do this in general? I mean, eventually, how do we know? So there's two possibilities. I'll leave this as a summary. In this case, you could find a smaller subset of S that actually generates the same subspace. What you ultimately want to get down to is a set where you can't reduce it anymore. So it would have the vectors, every vector is needed to generate a subspace. And if you try to eliminate a vector, it can't be done. And that's what we're trying to get to. And that's what's defined on page 37. So do the reading. I wish I could stay longer as usual, but as I say, I have a department meeting. If you're on the mailing list for the other class, I will be able to meet that office hour. So if you really want to ask other questions related to this or other problems, you're welcome. Well, if there's anyone not on the mailing list, give me your name quickly if you want me to add it to the mailing list so you can come today. Okay. No additions, so I think we're good. I'll see you next time. Sorry, I gotta run.
Thank you, Professor.
You're welcome.
Thank you, Professor.
Have a nice day.
You too.